to all of you. I welcome you to this Optica Student Chapter webinar. We have this chapter in the Department of Physics named IISER Pune Optics League. And as a part of this, we are organizing regular webinars and talks in the vast field of optics, 2D materials, material science, biophysics, etc. And as a part of this effort, today we have with us Dr. Saptarshi from Pennsylvania State University as a speaker. To give a brief introduction about Dr. Das, he received his Bachelor in Engineering in Electronics and Telecommunication Engineering from Jadavpur University, Kolkata. He then received his PhD degree in Electrical and Computer Science Engineering from Purdue University in 2013. He then worked as a postdoctoral researcher and an assistant scientific researcher in Argonne National Lab. Then he joined the Department of Engineering, Science and Mechanics at Pennsylvania State University in the year 2016, where he is an associate professor now. Dr. Das is also a recipient of Young Investigator Award from US Air Force Office of Scientific Research and also NSF Career Award in 2021. Dr. Das's group at Penn State leads a new multidisciplinary area of science, namely biomimetic sensing, neuromorphic computing, and hardware security, inspired by natural designs found in the animal world that allow evolutionary success in resource-constant environment. With this brief introduction, I would like to invite Professor Das to, if you can please start the talk.
Okay, thank you, Tamagna, for the introduction. And again, it's a great pleasure to be here with all of you today. And as Tamagna mentioned, the title of my talk is going to be a bio-inspired era for sensing, computing, storage, and security based on 2D materials and devices. And I think it's an optics society. So you will see that a lot of the work that we are doing is actually exploiting the optoelectronic properties of 2D materials. So a bulk portion of my talk is going to deal with optoelectronic properties of 2D materials. But before I do that, I mean, Tamagna already did the introduction for me, so I don't need to go through it really, very in detail. But I did my schooling in Calcutta from here school. Then I moved to Jadavpur University to complete my electronics and telecommunication engineering degree. After that, I went to Purdue for my PhD in electrical and computer engineering. And then finally, I did my postdoctoral research, and then I was assistant scientist there at the Argonne National Laboratory for a couple of years. And then I joined Penn State. Penn State, a little bit about Penn State. I mean, this is our mascot, which is Nittany Lion. I mean, Penn State is very well known for his football. We just had nice fall colors, we see very good nice seasons over here at Penn State. We are awaiting the snowfall over here. Hopefully we can escape. I'm going to India this winter, so I can escape some of the winter days. This is the institute where we primarily do our research. It's called Material Research Institute. It has two sides actually. One side is for material research and the other side for HUC, Institute of Life Sciences. The idea is to essentially bring material scientists and biological scientists close to each other so that they can collaborate. It's a highly interdisciplinary institute. We have most state-of-the-art, characterization, nanofabrication, and computation facilities. And finally, this is the department. This is my home department, although I'm affiliated with material science and electrical engineering department as well. I'd also like to acknowledge my different funding agencies, NSF, Army, Department of Defense, Department of Energy, Defense Trade Reduction Agency, and in fact, many private organizations, including the Semiconductor Research Corporation, which includes Intel, IBM, TI, and many other private entities. And of course, no research can be done without having a wonderful group. So I'm kind of really glad that we have a very talented and motivated pool of students who are always willing to take challenges and do very hard work in order to get the results. So of course, a big acknowledgement and big thanks goes to them. So now going into my technical part of the talk, first I would like to state what are the challenges that we are facing with today's technology. We all know that the silicon CMOS has been really tremendous in increasing the computational power that we have today. If you think about the supercomputers, their computing power is as good of a human being. If we continue to be on this trajectory, then by the year 2025, we will probably reach computing power, which is going to be equal to all of humanity combined. So that has been really amazing journey so far. But when we look into the supercomputers, we will find that they actually consume a huge amount of energy, close to 10 megawatts, and they also occupy a big area, almost close to 10 to the power 9 centimeters cube, which is the size of a football field. Compared to, if you consider brain as your ultimate computing tool, you will find that the energy consumption by brain is much smaller, almost 6 orders of magnitude smaller. And at the same time, it also occupies a much smaller area. So in terms of energy and area efficient computing, the brain is actually much superior computer compared to the conventional computing. And the primary difference is that biological computing is not von Neumann. So von Neumann computing is something where your central processing unit, where all the arithmetic operation like addition, multiplication takes place, is separate from the memory unit where you actually store the data. So anytime you want to perform some computation, you have to shuttle the data between the memory and the logic. And that actually becomes the main bottleneck, because this part consumes the most amount of energy compared to the actual logic operation that goes on into the arithmetic unit. Compared to the von Neumann architecture, brain is primarily non-von Neumann, because here the computing units, which are the neurons, are right next to each other, and these synapses through which the neurons connect with each other are essentially the memory element. So synaptic connection strength determines the weight of the synapse or the storage. In an adult human brain, you can find 100 billion neurons. Each neuron on average is connected to 1000 synapses. So there are almost 100 trillion synapses or storage units in the brain. So this is a massively parallel system which works on a non-von Neumann architecture, and that makes the brain extremely energy efficient. So therefore, our ultimate goal is to essentially derive inspiration from brain and make our devices or the next generation of technologies much more energy and area efficient. So therefore, we need really a rethinking, and we need innovations in materials, devices, circuits, architecture, and above all, in our approach in order to bridge the gap between the natural intelligence and the artificial intelligence. Now, one more thing that I would like to point out is that there is a lot of development today in artificial neural network, convolution neural network, deep neural network, but they primarily go by just the mimicking of the synapses connected to the other synapses. But when you consider the brain can do way more things than the artificial neural networks can do. In fact, if I think about, if I go beyond the human brain and look into the animal world, you will find that the animals can actually do amazing sensory computation. And I bring the sensor part because at the end of the day, when we are living in the era of this Internet of Things, where we have multiple sensors, which will be essentially connected over the internet, and most of the sensors are primarily going to be visual and audio sensors, which are going to collect the information. So if we can collect the information in a smarter way or process the information in the sensor itself, that can actually really reduce the burden on the computation on the cloud or in bigger computers. So our idea is to do in-sensor computing, and that is something the animals can do very well. And because of this amazing capability, animals can do much better than the human beings. For example, the spiders, these are the octopuses have polarized vision. And many of you may already know about that, right? We humans do not have that capability, but octopuses can detect polarized light. The spiders can detect micro vibrations. African bush elephants can smell water from a distance of 50 miles because they're living in very resource constrained environment. The barn owl can hunt in complete darkness, which means that it doesn't rely on its vision, but uses its auditory skill in order to find something. And the same applies to the catfish. In fact, the animals can do way better in terms of detecting magnetic field, infrared radiation, which we cannot do. Now, typically it has been believed that they have some special sensors, but with the recent development in the neurobiology or sensory neurobiology, it has been found that it is this architecture or the neurobiological architecture inside the brain of these animals, which actually helps them to perform this difficult computational or sensing task in a much more easier way or energy efficient way. And this is where we are actually deriving our inspiration from. And here I'm going to play a short video which will give you an overview of the type of work that we're trying to accomplish in our group.
It is pretty well known that animals can actually rely on their sensory skills in order to locate prey, find their predators, and even find their mates, which ultimately determines their evolutionary success. Now, what is very fascinating and sometimes very humbling to us is that they do it with minimum amount of resources. They consume very little amount of energy, and their tiny brains can perform computational tasks, which are essentially very difficult even for the modern day computers.
We are trying to mimic their functionality into our devices, and just learning about biology, how animals around us behave, is very interesting for me.
Nature is not only beautiful, but also it is very smart, and this is very deep-rooted in everyone who's working in this group.
We're doing something brand new. We're connecting nature and technology in a way that no one else quite has before.
So the primary focus of our research is to develop an unified platform for the next generations of ultra-low power and artificially intelligent sensors, which can not only sense the data from the environment, but can also process that information. It can actually store that information, and at the end of the day, it can also communicate that information among each other without compromising the security of the information.
So whether we're trying to sense a virus, sense an earthquake, sense changes in the climate, or critical risks that we face, having better sensors means better information, and better information means better outcomes.
These new sensors that we are developing in this era of Internet of Things is that there is so many of them. In fact, there will be almost like close to 1 trillion sensors by the year 2030, and each of them are going to consume energy. And the total energy consumption is going to reach almost 20% of the total energy expenditure that the human population uses. And unless and until we essentially solve this problem and make these sensors energy efficient, we will not be able to cope with these energy challenges. Really, if we want to move towards a sustainable future, we need to make sure that we make these sensors as energy efficient as possible.
Hope you like the video. So let me now move on with the rest of the talk. Sorry. So now I'm going to move into the the 2D material aspect, and I think many of you might actually be working on 2D materials. All of you are familiar with graphene, with which this area of 2D material actually started. There is also more, interesting materials like hexagonal boron nitride. Graphene is a conductor. HBN is an excellent insulator. And then you have these semiconducting 2D materials, which are these transition metal dichalcogenides. And if you look into the periodic table, you will find that there's a wide variety of them. These materials, as you know, I mean, they can be mined. They are van der Waals materials, which means they have weak weak outer plane bonding, which allows you to exfoliate these materials into very, very thin layers. And at the end of the day, we are interested in this material because these materials allow us to scale the transistors or the next generation of devices much aggressively than what we could do with silicon. And the primary reason for that is, even the most advanced silicon FinFETs use a 6 nanometer body thickness, while the monolayer of 2D materials can be 10 times much thinner. And because it is much thinner, they can also be made much more smaller, and therefore you can have more and more devices to increase your computational power. So that's why 2D materials are intrinsically way more attractive for us to make, ultra scaled or aggressively scaled devices. So in our group, we work with a wide variety of 2D materials. These are some of our old results when we were working with exfoliated single crystal flakes. And you can clearly see that these transistors made out of these 2D materials do show very decent performance. In fact, the on current can actually reach as good as the current silicon FinFET technology. In addition to that, they offer, decent mobility numbers, and subthreshold values, which are very close to the ideal number of 60 millivolts per decade. But then again, exfoliated single crystal material is not how a technology can be developed. And in this context, we actually collaborate with a lot of wonderful colleagues that I have at Penn State, who are actually trying to grow these 2D materials over a large area using various techniques, starting from CVD, MOCVD, PVT, as well as even low temperature ALD techniques, using a wide range of temperatures, in order to enable both back end of the line as well as front end of the line integration, or integration with flexible substrate or substrates like glass, which have temperature limitations in terms of their thermal budget. And then